Welcome to this Masterclass Explainer. Today, we're conquering the periodic table, its core properties, and the precise variations that literally govern our physical world. We're going to break down this incredible scientific architecture piece by piece. The periodic table is the ultimate master key to understanding the universe, allowing you to predict the behavior of every single element on Earth. We are shifting entirely from rote memorization to pure logical deduction today. By decoding its fundamental structure, you're going to master the physical and chemical properties of chemistry and honestly never have to blindly memorize again. Okay, let's dive right into this because this specific paradigm shift, it's an absolute favorite for ICSE examiners. So, for a long time, early scientists like Mendeleev tried arranging elements by increasing atomic mass, which is essentially the weight of the atom, but, there were inconsistencies. It wasn't until Henry Moseley came along and rearranged everything by atomic number, the exact number of protons an atom has, that everything clicked perfectly into place. That one massive shift gave birth to the modern periodic law.
Here is our roadmap for today. First, we decode the grid, groups versus periods. Second, we build your arsenal of core definitions. Third, we reveal the trend tracker. Fourth, we look at the why behind those trends. And finally, we'll wrap up with your ICSE exam essentials.
All right, part one, the grid, groups versus periods.
The rules governing this grid are actually incredibly simple. The vertical columns, those are called groups. There are 18 of them, and they're super important because they dictate the number of valence electrons. That's just the electrons in the outermost shell. If you're in group 1, you have one outer electron. Simple, right? The horizontal rows are called periods. There are 7 of those, and they reveal the exact number of electron shells an atom possesses. So period 3, that means 3 shells. It really is that beautifully logical.
Moving on to section 2, the arsenal, core definitions.
First up is atomic size, or atomic radius. I want you to picture an atom with a dense, heavy nucleus right in the center, with rings of electrons orbiting it. The atomic size is simply the physical distance from the absolute center of that positive nucleus straight out to the outermost electron shell.
Next is metallic character. This is the tendency of an element to lose electrons to form positive ions, or cations. Metals absolutely desperately want to shed those 1, 2, or 3 outer electrons so they can achieve a perfectly stable, noble gas-like configuration. And when they throw away a negative electron, they become positively charged.
In direct contrast, we have non-metallic character. Nonmetals are hungry. They've got 5, 6, or 7 electrons in their outer shell, and their absolute driving tendency is to pull in extra electrons to complete their octet. When they gain these negative electrons, they form negative ions, which we call anions. So, the crucial point is right here with ionization potential, or, sometimes you'll hear it called ionization energy. Imagine you want to steal an electron from a perfectly neutral, happy atom. It's not going to just let it go without a fight. Ionization potential is the exact amount of energy you must put into the system to forcefully rip that outer electron away.
Now flip that concept perfectly in reverse for electron affinity. This is the energy that's given off, or released, when a neutral gaseous atom successfully captures an added electron. Think of the word affinity as love or attraction. When an atom that loves electrons finally gets one, it releases a burst of energy and satisfaction.
Finally, we've got electronegativity. Picture a microscopic chemical tug-of-war. 2 atoms are sharing a pair of electrons in a covalent bond, but they rarely share equally. Electronegativity is the tendency of an atom to violently pull that shared pair of electrons toward itself. It's a dimensionless property, kind of like a ranking system, and fluorine is the absolute reigning champion of the entire periodic table here, scoring an impressive 4.0.
All right, section 3, the trend tracker.
Every single trend we're about to discuss anchors back to an epic, high-stakes battle between 2 massive forces. On one side, you have the nuclear charge, that's the positive protons in the center, desperately pulling all the electrons inward. On the other side, you have the number of shells, the physical addition of new electron layers, pushing the boundaries of the atom further and further out.
Here are the raw facts of the trend tracker. As you move across a period, from left to right, the atomic size decreases, metallic traits drop, and non-metallic traits absolutely soar. Conversely, when you move down a group from top to bottom, the atomic size massively increases, and metallic traits get a huge boost. But remember, we don't memorize here, we deduce. Which brings us right to section 4, the why behind the trends. Let's walk through the exact mechanics of what's happening when you travel left to right across a period. As you step from one element to the next, you aren't adding new shells. You're actually just adding more protons to the nucleus and more electrons to the exact same outer shell. Because the positive protons are increasing, that nuclear charge gets incredibly strong. It acts like a super powerful magnet, pulling those electrons tighter and tighter toward the center. As a result, the atomic size shrinks. And because the atom is holding onto its electrons so tightly, it becomes way harder to remove one, meaning ionization potential shoots straight up.
Now let's see how this dynamic completely flips when you go top to bottom down a group. With every single step down, you're adding a completely new physical electron shell. The distance from the nucleus to that outermost shell increases drastically. So even though there are technically more protons, the sheer physical distance completely outweighs the nuclear pull. The atomic size just balloons outward. And because those outer electrons are now so far away from the positive nucleus, they're barely holding on. That makes it incredibly easy for the atom to lose them, which is exactly why a metallic character increases as you go down a group.
And finally, Section 5, ICSE Exam Essentials. First up is the inert gas exception. Group 18 elements, the noble gases, have a perfectly complete outer shell, a full octet. Because their shells are already full, they absolutely refuse to play the chemical tug-of-war. They don't want to lose electrons, and they certainly don't want to gain any. Therefore, their electron affinity is practically zero. They're basically chemically inactive. Always remember this exception when plotting trends on an exam.
Next, you've got to contrast the two extremes of the table. Over on the far left, you have Group 1, the alkali metals. They have exactly one electron in their outer shell, and they are totally desperate to lose it, making them the most reactive metals. On the far right, just before the noble gases, you have Group 17, the halogens. They have 7 outer electrons and violently want to gain just one single electron to complete their shell, making them the most reactive nonmetals. It really is a perfect pairing of opposites.
And that brings us to our final challenge. Imagine an exam question gives you a completely unknown element, telling you only that its atomic number is 20. Could you use our master formula to deduce its traits? Let's do it. An atomic number of 20 means 20 electrons. Configured, that's 2, 8, 8, 2. 4 shells means it sits right in period 4. 2 outer electrons means it sits in group 2. That makes it an alkaline earth metal, specifically calcium, ready to lose 2 electrons and become a positive cation. No table required, just pure structured deduction. You now literally hold the master key to the elements. But ask yourself, as scientists synthesize new, massive super-heavy elements in labs, elements like oganesson at atomic number 118, are these fundamental trends going to hold up, or will the rules of the universe break down at the extremes? Keep exploring, and you'll never look at chemistry the same way again.